In mathematics, a proof by infinite descent is a particular kind of proof by contradiction which relies on the least integer principle. One typical application is to show that a given equation has no solutions. Typically, one shows that if a solution to a problem existed, which in some sense was related to one or more natural numbers, it would necessarily imply that a second solution existed, which was related to one or more, smaller, natural numbers. This in turn would imply a third solution related to smaller natural numbers, implying a fourth solution, therefore a fifth solution, and so on. However, there cannot be an infinity of ever smaller natural numbers, and therefore by mathematical induction the original premise, that any solution exists, is incorrect. Its correctness produces a contradiction. An alternative way to express this is to assume one or more solutions or examples exists. Then there must be a smallest solution or example, a minimal counterexample. We then prove that if a smallest solution exists, it must imply the existence of a smaller solution, which again proves that the existence of any solution would lead to a contradiction. The method of infinite descent was developed by Fermat, who often used it for Diophantine equations. Two typical examples are showing the non-solvability of the Diophantine equation R2 plus S4 equals T4 and proving Fermat's theorem on sums of two squares, which states that an odd prime p can be expressed as a sum of two squares only when p1, in some cases, to the modern eye. His method of infinite descent is an exploitation of the inversion of the doubling function for rational points on an elliptic curve E. The context is of a hypothetical non-trivial rational point on E. Doubling a point on E roughly doubles the length of the numbers required to write it, so that halving a point gives a rational with smaller terms. Since the terms are positive, they cannot decrease forever. In this way Fermat was able to show the non-existence of solutions in many cases of Diophantine equations of classical interest. Number theory. In the number theory of the 20th century, the infinite descent method was taken up again, and pushed to a point where it connected with the main thrust of algebraic number theory in the study of L functions. The structural result of model, that the rational points on an elliptic curve E form a finitely generated abelian group, used an infinite descent argument based on E2E in Fermat's style. To extend this to the case of an abelian variety A, André Weil had to make more explicit a way of quantifying the size of a solution, by means of a height function, a concept that became foundational, to show that A2A is finite, which is certainly a necessary condition for the finite generation of the group A of rational points of A. One must do calculations in what later was recognized as Galois cohomology. In this way, abstractly defined cohomology groups in the theory become identified with descents in the tradition of Fermat. The Mordell-Weil theorem was at the start of what later became a very extensive theory. Application examples. Irrationality of square root 2. The proof that the square root of 2 is irrational was discovered by the ancient Greeks, and is perhaps the earliest known example of a proof by infinite descent. Pythagoreans discovered that the diagonal of a square is incommensurable with its side, or in modern language, that the square root of 2 is irrational. Little is known with certainty about the time or circumstances of this discovery, but the name of Hippasus of Metapontum is often mentioned. For a while, the Pythagoreans treated as an official secret the discovery that the square root of 2 is irrational, and, according to legend, Hippasus was murdered for divulging it. The square root of 2 is occasionally called Pythagoras' number, or Pythagoras' constant, for example Conway and Guy. The ancient Greeks, not having algebra, worked out a geometric proof by infinite descent that may be more accessible. The following is an algebraic proof along similar lines. Suppose that square root 2 were rational. Then it could be written as for two natural numbers, p and q. Then squaring would give, so 2 must divide p2. Because 2 is a prime number, it must also divide p by Euclid's lemma. So p equals 2r for some integer r, but then which shows that 2 must divide q as well. So q equals 2s for some integer s. This gives. Therefore, if square root 2 could be written as a rational number, it could always be written as a natural number with smaller parts, which itself could be written with yet smaller parts, ad infinitum. But this is impossible in the set of natural numbers. Since square root 2 is a real number, which can be either rational or irrational, the only option left is for square root 2 to be irrational. Irrationality of square root k if it is not an integer for positive integer k. Suppose that square root k is not an integer, but is rational and can be expressed as n for natural numbers m and n, and let q be the largest integer no greater than square root k. Then the numerator and denominator were each multiplied by the expression, which is positive but less than 1, and then simplified independently. So each of the two resulting products is itself an integer. Therefore, no matter what natural numbers m and n are used to express square root k, there exist smaller natural numbers m less than m and n less than n that have the same ratio. But infinite descent on the natural numbers is impossible. So this disproves the original assumption that square root k could be expressed as a ratio of natural numbers. Non-solvability of R2 plus S4 equals T4. The non-solvability of integers is sufficient to show the non-solvability of integers, which is a special case of Fermat's last theorem, and the historical proofs of the latter proceeded by more broadly proving the former using infinite descent. The following more recent proof demonstrates both of these impossibilities by proving still more broadly that a Pythagorean triangle cannot have any two of its sides each either a square or twice a square, since there is no small as such triangle. Suppose there exists such a Pythagorean triangle, then it can be scaled down to give a primitive Pythagorean triangle with the same property. Primitive Pythagorean triangle's sides can be written as, with a and b relatively prime and with a plus b odd, and hence y and z both odd. There are three cases, depending on which two sides are postulated, to each be a square or twice a square. Y and z, neither y nor z, being odd, can be twice a square, if they are both square. The right triangle with legs and an hypotenuse also would have integer sides including a square leg, and would have a smaller hypotenuse. Y and x. If y is a square and x is a square or twice a square, then each of a and b is a square or twice a square, and the integer right triangle with legs and an hypotenuse would have two sides each of which is a square or twice a square, with a smaller hypotenuse than the original triangle. Z and x. If z is a square and x is a square or twice a square, again each of a and b is a square or twice a square, and the integer right triangle with legs and an hypotenuse also would have two sides each of which is a square or twice a square, and a smaller hypotenuse. In any of these cases, one Pythagorean triangle with two sides each of which is a square or twice a square has led to a smaller one, which in turn would lead to a smaller one, etc. Since such a sequence cannot go on infinitely, the original premise that such a triangle exists must be wrong. This implies that the equations n cannot have non-trivial solutions, since non-trivial solutions would give Pythagorean triangles with two sides being squares. For other similar proofs by infinite descent for the n equals 4 case of Fermat's theorem, see in other reading. Infinite descent at planetmath.org. Example of Fermat's last theorem at planetmath.org.